Thanks a lot. There's nothing like being the guy who's seeing you guys on lunch. I'll try to be quick here. Okay, excellent. As I said, I'm Martin Vroegh, the environmental manager. I look after sustainability type projects for our industry. And working with Biofuels, I'll get into a little bit. I think, I don't know if I'm going to be able to make cement really sexy in this presentation, but hopefully you guys will think of cement and how we fit into the energy world a little differently. So a little bit more about us. We're part of a large Brazilian family-owned company, privately owned. We're called Darlington. It's one of the largest Latin American companies in the world. We're into energy. We operate 36 hydroelectric power stations in Brazil, where we're the largest producer of orange juice in the world at 35% of the world's orange juice. If you consider Florida produces 6%, just to put it in perspective. Into agrochemicals, metals like aluminum, cement, various things, pulp and paper. So it's a very large corporation, and St. Mary's Cement is a small facet of that. And you can see in our North American operations, St. Mary's Cement fits in there in the middle. So we operate 2 cement plants in Ontario, 1 in Michigan, 1 in Illinois. We're celebrating our 100th anniversary this year, and a little interesting story. The Rogers and the Lind guys, the founders of the company, actually made their money in the Klondike Gold Rush, came back to their hometown in St. Mary's, Ontario, and bought the largest business in town, the local stone quarry. And eventually that evolved into St. Mary's Cement, with the help of one of the private investors, Gooder and Ward. So there's a little bit of whiskey involved in all that. So anyway, back to this. I'm going to talk a little bit about cement and it going into concrete. And that's a pretty profound statement there, that after water, concrete is the second most consumed substance on the planet. And it's important that you understand a little bit about cement, because a cubic meter of concrete contains 300 kilograms of cement. And cement is the glue that holds sand and gravel together, and water, it doesn't wet the mixture, it actually becomes part of it chemically, and it acts like the catalyst to the glue. So I'm going to take you to some cement 101. I'm trying not to be a bad teacher like Cameron Diaz and Bad Teacher there. So I'm going to talk a little bit about manufacturing cement. That is a cement truck, despite the fact that 99% of everybody thinks that is. So that's a concrete truck. The cement truck holds powdered cement. And what comes out of the concrete truck is concrete. Okay, so now that you know that, making cement produces large quantities of greenhouse gas. That's I guess the Achilles heel of cement manufacturing. And 2 sources of greenhouse gas are fuel and calcination. Now what's calcination? Calcination is when you take limestone, which is calcium carbonate, and you add heat to it, and you get lime, calcium oxide. That lime is what we make the cement out of, and CO2 is what comes out of the stack. The average Canadian cement plant, the average in the industry, is around 900 kilograms of CO2. For our company, we operate the 2 lowest greenhouse gas intensity cement plants in Canada. Our average is around 750 kilograms per ton of cement. So 3/4 of a ton of CO2 goes out the stack for every ton of cement that goes out the gates. And so that's a huge amount of CO2. And it works out to about 5% of the world's CO2 from man is coming from cement. So this is a nice little bit the Discovery Channel did at the Bowmanville cement plant. And basically, in a nutshell, it's going to say that we take rock out of the ground, we crush it up into very, very fine powder with big machines. These machines, this machine here is about 4,500 horsepower motor on that. So it's a pretty big motor. It grinds it up into a very fine powder, like talcum powder. And that talcum powder, right there, you see, that's limestone dust. It gets put into this big preheater tower. That's the one you see on the skyline of Clarington. So the exhaust gases are coming out of the kiln, and we actually recover that energy by preheating that limestone up into very high temperature. So if you look at those Dyson vacuum cleaner ads, those are kind of mirroring this technology, utilizing this type of technology to de-dust and to concentrate the heat. We get the heat from burning fossil fuels. We burn a lot of fossil fuels. Bowmanville plant here burns about 30 tons an hour of petroleum coke. That's a lot of energy. 92% of the energy we consume from a gigajoule basis is coming from fossil fuels and used directly. So that's a shot inside the kiln of the thermal camera. So if you think of that kiln, it's kind of like taking a paper towel tube, putting sugar in one end, putting it on a little angle and rotating it, and then the sugar will move from one end to the other. So that's all that we're doing, but we're doing it in ginormous scale. And you can see there that things are pretty hot. We take the stuff out of the kiln, we grind it up again in the presence of gypsum in these big ball mills. These things contain grapefruit-sized balls that just smash around and smash it into a powder. And then voila, the cement truck picks it up and drives away with it and delivers it to the concrete trucks, where we mix it with sand, gravel, and water. Okay? So some other key environmental stats are, it takes, for every 10 tons of cement, it takes 1 ton of fuel. 1 ton of fuel makes 2.7 tons of carbon dioxide gas. Limestone is about 38% CO2 by mass. So that's a lot of CO2 that gets released in every single ton of limestone. And 1 to 2 kilograms of NOx and SO2, which are smog and acid rain chemicals, come out with every ton of cement. 60% of all of our greenhouse gas produced comes from the limestone, and only 40% is coming from the fuels. So where you can be as efficient as possible and try to reduce fuels or try to find greener fuels or carbon neutral fuels, that doesn't help to fix the problem that's coming from the limestone. It's how do we solve that big problem? So some of the things we've done is we've looked at cementitious materials. Wastes from the steel industry, like slag and fly ash from coal-fired power stations, can be used and mixed in with cement into concrete and reduce the amount of cement needed by as much as 50%, which reduces the greenhouse gas by 30 to 50%. That's a huge savings in greenhouse gas emissions by utilizing two wastes that would otherwise have to find landfill for. Other things we do, alternative raw materials. We can use other raw materials rather than using virgin raw materials. So we can try to reduce our footprint by indirectly reducing the amount of transportation distances and things like that, and utilizing things like flue gas desulfurization gypsum. We have to add gypsum in, but we can take some flue gas desulfurization gypsum, which comes as a waste of scrubbers from, say, coal-fired power stations. We can mix that in, and it substitutes gypsum. So these are some of the things we can do. Foundry sand from here at Bowmanville Foundry. After they make sand castings and stuff like that, we can take some of that and substitute that in as a silica and iron source and use that for manufacturing cement. So that's how we can help also make ourselves more sustainable. Energy conservation, a big one here in Bowmanville. We're one of 10 companies making a difference on the SciPec Task Force annual report that came out from the Natural Resources of Canada. And also, the Bowmanville cement plant here was the first facility of any kind in North America and South America to achieve the ISO 50001 Energy Conservation and Management Standard. And still the only one in Canada to have that. So it's a pretty impressive goal here with the help of 360 Energy on achieving that. Product innovation. The industry got together to develop together a new cement standard that we are actively pushing and marketing, which what it does is it contains about 10 to 15% interground limestone into the cement product. That reduces the amount of material that has to go through the kiln by 15%, which reduces greenhouse gases by 15%. And for what it might weaken the glue effect of the cement, it actually increases the strength equivalently by having microfine sand particles. So that microfine aggregate that you put in offsets any dilution factors. So that product is something that we're working well with now on procurement of governments, which buy about 60% of our product through municipal and provincial infrastructure, that we want them to be the kickstart catalyst to utilizing these products more. Low carbon fuels, utilizing things like plastic bags. We did a trial at our St. Mary's, Ontario plant. At the temperatures we're burning at, over 1400 degrees Celsius, it thermally destroys any organic molecule. There's absolutely absence of any harmful, toxic organic molecules. And so these things that would otherwise be sent to landfill and waste can be utilized as a fuel that is actually much more highly refined than things like petroleum coke, which is bottom of the barrel, literally, and 82% carbon coal. these things are unrefined natural resources that are in limited supply. And if we can utilize things that have already kicked the can and would otherwise just be thrown in the trash, that's far more sustainable. So these things make us more sustainable, and it's very important for us, but they don't necessarily, it doesn't do everything for us. It doesn't solve that problem with what do we do with the limestone. And it's one thing to be sustainable, it's different to be environmental. And environmental is not necessarily economical. It's important that we understand 3 points to the triple bottom line of sustainability, being socially sustainable, environmentally sustainable, and economically sustainable. Without any one of those, you won't be around. It's one thing to be environmentally friendly. It's one thing to be environmentally friendly, but if you can't do it economically, you're out of business. If you can't do it and be in a social manner, when the public doesn't want you around, regardless of how much money you may make or how environmentally friendly you are. So it's very important to understand triple bottom line sustainability. And in so doing that, it becomes very important for our industry and for our company to let people understand the life cycle analysis of the products and the projects that come from our building materials, because the types of things that are made from cement are very important to the standard of living that we have today. It's so ubiquitous, this concrete. You're in a concrete building standing on a concrete floor. Those are the things that everybody takes for granted, that's coming from things like the cement plant next door here. Other big things that people see is when people talk about sustainable energy and renewable energy, they don't really realize that 870 cubic meters of concrete is required for every 1 megawatt of output power. You've got to hold those things to the ground or they're just going to fall over, and you do that with concrete. So 1,500 ton foundations, as well as all the steel, aluminum, magnesium, glass, and carbon that goes into these, and the greenhouse gases that come out for every ton of that. That's a lot of emissions, 208 to 340 kilograms of CO2 per cubic meter of concrete alone. So these things start at a deficit on the greenhouse gas that they can offset, and they have to work for a long period of time before they can actually break even on their greenhouse gas footprint. So how do we make these projects more sustainable? And why should we, as a cement industry, be worried about that? Well, we're worried about it because we use huge amounts of energy, and I'll get into that a little bit later. The partnership we have with Biofuels here is an interesting one. We saw that we produce huge amounts of greenhouse gas, and if we want to be sustainable, we better find a way to deal with that greenhouse gas. Now, there are other things you can try to do with it, but they produce a waste. If you produce a waste, you now have a waste problem. You now have trucks leaving with waste. What do you do with that? So we have to try to find something that doesn't involve that. So one of the things about algae is it's one of the fastest growing organisms in the world. It consumes twice its weight of CO2 every day. And it's one of the best CO2 scrubbers on the planet. Okay? It just eats up CO2. If you look at algae for generating biofuels, by far it blows away everything else on the planet that we think of. And not only that, but it doesn't compete with crops for food. So the food crop argument doesn't get involved when you talk about algae-based biofuels. So you're talking about producing between 10 and 13,000 gallons per acre per year versus corn is 300. So if we look at our St. Mary's, Ontario plant, not Bowmanville, St. Mary's is where we're doing the pilot study. So this pilot plant is on this cement plant here, and we're doing it here in this building down here on the right. But we produce 720,000 tons a year of cement out of that plant, 540,000 tons of CO2 emissions. That's a lot of CO2. So how does the algae do it? What does algae do? Well, algae is it's basically a plant, but a single cellular plant. And it's photosynthesis. It takes the energy from the sun or from artificial light, and it will consume that by breaking the CO2 into oxygen and carbon. It uses the carbon to manufacture itself as a carbon-based organism and releases the oxygen. And from that, we can then split that, harvest the lipids, the oils, and manufacture things like biodiesel and glycerin. So how do we get down to this? One of the things that when we got into this project, we thought, okay, well, there are a bunch of companies that are out there doing algae, and we looked at them and they talked about, oh, we've got algae growing in a beaker, so maybe we'll build a beaker so big that it'll, you know, work for your cement plant. We kind of went, I don't know. So we wanted to these guys approached us and they said, we want to scale down existing processes. Look at big industry and scale it down. We want industrial solutions. We don't work in a sterile environment. I mean, a cement plant, a surgical instrument is a sledgehammer, right? It's not a very sterile environment, big industrial stuff. We want to work with a local algae species. We want to make the worst environmental hazard be, you know, the equivalent of spilling a little bit of grass seed on the lawn. We didn't want to get into you hear about people biologically altering algae species for maximizing oil and stuff like that, but there's a reason why we don't do it. The potential for ecological issues that we don't want to get into. And second of all, there's a reason our algae species that we selected, which is the same one you find in a puddle outside, literally. We picked that because it's had a couple billion years of evolution to say that it's the best species out there right now anyway. We wanted to avoid permitting delays in our project, so we went with a very small scale at the maximum that we would be allowed to do without having to go down multiple years of permitting delays. We wanted to find a solution today, not get caught up in something where nobody at the Ministry of the Environment has ever heard of anybody doing an algae project on stack gas, so they scratch their head and wait 2 or 3 years. We didn't want to get into that. We understand that we manage a microecology because we can't operate a sterile environment. It's the same thing. You may see a pine forest of beautifully planted trees, but what you're not really paying attention to is the fact that there are little shrubs, there's birds, and there's bees flying around pollinating things. We have to have the same sort of health in our algae farm to make sure that we have a microecology going there. And that's what gives us a very healthy system. We want it off the shelf wherever possible. So we wanted to make sure that our relationship with Pond Biofuels did not pay for them to go invent all sorts of stuff that already exists. And winter and nights, it was an important thing. We operate 24 hours a day, 330 days a year at our cement plant. So we don't shut down except for twice for maintenance a year. So the only thing you're doing if you have open ponds is playing hockey on them in the wintertime. And if you covered them in tubular bioreactors, which some of you may have seen if you're into the biofuels scape, is we would have needed over 300 acres of space versus the project we're doing at Pond Biofuels will take up about 15 acres. So the difference there is huge, and the implications are huge because that makes this technology very implementable on existing facilities with the existing real estate that exists. So minimal footprint being important to us, and also to include academia wherever possible. We don't want to be, you know, in our partnership with Pond Biofuels, we didn't want to be paying for their PhD, so to speak. We wanted to make sure that people who are working towards their PhDs are given opportunity to help do and conduct their research with us. So we sat around and said, okay, how do we start this project? How are we going to get the smokestack gases out? So a few years later, on a couple of napkins, we drilled a hole into the side of the smokestack.